Okay.
Right.
Alrighty.
Yeah, okay.
Welcome to SDPHP. Here is our very normal social system, our website, our meetup page, and our Twitter. We are barely on Facebook. We are kind of on IRC.
We're trying to get back.
We're trying to get back. We're trying to push IRC a little more. And we are on Slack still. If you have any questions about the URLs here on the slide is posted on the sdphp.org website. So it's very easy to pull up. I don't know if these job postings are still legitimate. You'd actually know better than I would. Still working.
Actually, I don't know.
So, unfortunately, the two people who helped me out through this process are unavailable with baby and vacation. So I don't know if the job postings are current or not, but they do get updated on the slides. So if you pull up the slides off the website, then you'll see the updated job postings. And the job postings do get put on the website. For September 14th, Evan is going to be presenting Elasticsearch at Zito Media. That's our downtown meetup. And this is, of course, the current meetup that you're at. The next month's meetup will be Postgres, a different Postgres presentation than the Zito Media Postgres presentation. So if you've seen that one, this one will be different. Different presenter, different subject. And the next San Diego Laravel meetup will be August 24th. We'll be covering everything that was discussed at Laracon this year with Eric this time. Speakers, aside from myself, new speakers get a free SDPHP high class. We are looking for speakers. If you have something interesting to present, please let me know. You don't have to be an expert. You just have to be willing to learn and share your learning. Eric, John, and I do the PHP Ugly podcast. Record every Thursday and publish every Saturday. We recently had a professional group edit our podcast. It sounds exactly the same as us having not paid for it. So don't think we'll be doing that again, but if you want to hear more of what I have to say and some of Eric and literally none of John.
There's an error in your array.
Yes, there is. As always, huge thank you to business.com for providing beer, food, space, and time. Without them, we wouldn't be here, wouldn't have SDPHP.org, so huge thank you. The same goes for Zito Media for our downtown presentations. I don't go to the downtown ones, but they provide a huge benefit to us, space and time, and it's fantastic. And the Diego Dev Group for supporting the pregame and many of the people present. And that's it for the intro slides. So I think we're gonna break down and try to get good. So, does everyone here use Git? Does anyone here not use Git? So everyone here has the basic push, pull stuff. It's good. Because this is not the basic stuff. So the first thing we're going to look at is the history of version control systems. And interrupt at any time if you have any questions. This is an area that I'm researching quite a bit, so just hand up and I'll call you. So first we had file locking version control systems. This included RCS and SCCS. If you're old enough, remember these. I've actually used a couple of these. Then we got these multi-user diff-based systems. It might sound weird that I'm saying that diff-based is a specific branch of things here, but you'll see what I mean later. So we had CVS, and then built off of CVS was Subversion. Now we have distributed. So distributed version control. So this includes Git, which we're talking about today, and Mercurial, which is so close to Git that it's almost part of this talk, but it's just different enough in its internals that we're not going to cover it. So Git is easy. See, Git gets easier once you get the basic idea that branches are homeomorphic endofunctors mapping submanifolds to the Hilbert space. We're going to go back to this slide later, because it's going to be funny for a different reason. Because Git really is easy. So the first thing we're going to look at is the locking flow, the RCS type flow for files. You used to check into a server and say, I want to edit this file. And it would give you that file. And as long as you had that file, no one else could check it out. You would try to say, CO, check out this file, and it would say, Tom already has it.
And you go yell, Tom, say,
No.
shut the
So
file
I'm on a
back in.
vacation for a week.
There were, oh yes, there was CO override. You had to kill people's keys. You had to have a manager you could go to provide your override code. So this is an old system. Now we got the multi-user flow, which is actually still a modern system as much as it's not great. It's the tools that aren't great, not the system itself. So I can still check out a file, and then someone else can still check out a file. And then we can merge our file back together, making a whole new file on the server. And it still works relatively well, it's just that the tools have gotten stale. Now, Git is different, but the same. It's different in that you're doing the same sort of behaviors, but it's a lot more complicated. We're checking files in, checking files out, creating branches independently of each other, doing things wholly separately, merging back in the middle in our server here. Lots of different behaviors, but surprisingly similar to the non-distributed format, to the diff-based system. But Git is not a diff-based system. Git does not store diffs. Git does not keep diffs. If you have file 1 and file 2, and only line 1 changes, you still have file 1 and file 2 in Git. It doesn't just keep file X and then change. It has a copy of both files. So we're just going to quickly go over the real basics of Git storage. Most of this should be pretty simple for anyone who's been using Git in the past, but this is just to make sure that you're ready for the next slide. So Git clone and Git pull, same behavior here. Git clone creates a repository from scratch. Git pull just updates a repository. What it's doing is pulling here into your local storage, staging, and then working areas. Git fetch just takes the remote data and updates your local repository. Not necessarily your branch that you're currently working on. It just says, make sure that my server is up to date with the parent server. Git add moves from your working area into your staging area. This is an important delineation line, is that a staged file is in a very specific working area called index. The staged file is in a locked position that is being tracked very differently than unlocked, unstaged files. We'll get into that further. Now, Git Commit takes your staged stuff, pops it into your local Git repository. It says this stuff is locked. Here's a commit. I'm making a record of the state of things that were in staging, locking them down. And then Git push just does the inverse of Git fetch, which makes sure that the remote directories are in sync with your directory. Now, Git Checkout Head. This is something you'll encounter if you ever screw something up or you're just playing around and you want to undo what you're doing. Git Checkout Head will take a single file, and or Git Checkout Head will take either a wildcard or a single file and bring it back to your working directory from the state that it was in your local repository. So if you have something that you've changed, you want to go back to the way it was on the commit that you're on, you go Git Checkout Head. Head is a confusing term, but we're going to break down head piece by piece later on. Git Checkout just says unstage. Take something that I said was ready to commit, take it back. Don't commit it if I say commit. And finally, Git diff. This compares what you've got in your working directory with what you have in your local repository. This is a really simple tool for writing your commit logs. It just says, here's what's changed. Now, one of the things about this tool is people think Git diff. People think that diff files on the way that Git stores changes. Git stores files. But Git doesn't actually care about diffs in any regard whatsoever. Diffs are wholly irrelevant. All Git cares about is files. That's the beginner section. You guys ready? I love audience participation. So, we're going to make a directory for our Git project called Inside Git. Let's cd into it and type git init. Okay. Now, it just says initialize empty Git repository in yada yada inside git.git. So now we have our .git directory. What's in there? So let's ls it. We have .git, and inside of .git, branches, config, description, head, hooks, info, objects, and refs. So for initialization, we've just got an empty repository. An empty repository mandatorily has all of these in them. Now for Git, there's only one Git directory at the root of your project. SVN has a root directory, has a hidden directory at the root of every file, every folder. Git's just got the one. So the first thing we're going to look at within this directory is objects. Because objects is the stuff, is the contents. So, hopping into Git init, let's go into objects. It's ls, objects. We've got info and pack directories. So let's echo test object1 to object1.text. Remember, this is in the inside Git directory, not in the .git directory. So we're making my first file that I'm going to do something with and track. The contents of the file is test object1. The name of the file is object1.text. Now I'm going to say git hash object object1.text -w. So I know the confusing part about this is the -w. -w means write the file to the file system. Git hash object means give me a SHA-1 hash of the file. Object1.text is the file I want hashed. So all I'm doing here is generating a SHA-1 hash of the file and writing that file into the Git objects directory. We can see that further here if I ls the directory that it got written into. Now, you'll notice it returned this giant string of text here, 62D, 62D0E4E, yes. So the directory here for the object is 62, the same as the first two characters of the SHA-1 hash of the object. And then the file inside that directory is D0E4E, the rest of the characters of that SHA-1 hash. Right? So all it did was take this file, rename it, and move it. If I say git cat file, and then this is called a short SHA, so because a SHA is such a unique hash, I can just give it the first part of the name, and we'll figure out the rest. So cat file means read the file. Git objects are stored in peculiar ways. We'll get into that later too. But for the purpose of this, we're just reading straight out of the text file that got written there, printing P to print to screen, test object 1. It's literally just the file that I made, moved to a different directory. Now it's named in a weird way, but it's the same file. So now let's echo version 2 to the same file. Git hash object, object1.text, -w to write it. Now without the -w, I'd still get the string, but the file wouldn't have been moved to the directory. It wouldn't have been renamed and moved, or copied and moved. So now I've got a new SHA-1 hash. And if I go and look at that new directory and that new file, I get the new version of my object. Now both of these exist simultaneously. All I've done is add something into the Git storage system. I just said, yeah, put this file in Git, store it for a while. This is my local Git repository. This is not staging area. This is the Git local. I'm writing to the .git directory. Does that make sense? So at this point, all I'm doing is using a creative way of renaming files and moving them around to store the file that is your programming code. Both of these files exist at the same time. They're not tied to a commit. I've said, store this and store this. Now I have 2 additions in my local Git. But fortunately, nothing points to these files. They're just stored there for now. So it's just my local version that just knows about these. So the next step is committing these files. Everyone's familiar with the process of committing and pushing. So I've got one object, object1.text. So I've got this command here, git update index. So index, remember, is our staging area. It's that gray area between what I'm working on and what the .git directory is. It's what I'm ready to commit. So that index, that sort of working Git space, I want to update it. I want to add a file. And cache info is how you specify the information about the file you want to add. Okay, so for my purposes, 100.644, that is a file permission. That is me saying this is a text file, non-executable, accessible by everyone, etc., etc. This is a basic file permission. 1F7A, 7A for yada yada, and that's the SHA for the file that I got earlier. 1F 7A 7A 472. So when I asked Git to give me an object, it made an object and gave me the SHA. So now I'm going to say that's the object I want to commit. So I give it the SHA, and then I give it the name of the file. And yes, this is the totally worst, most manual, hands-on way to do it. Right? You're not going to do this. Now, I say Git write tree. And this brings us to the part about Git that no one knows about. The part that's most important that doesn't get covered in basic Git knowledge. I don't know why, because it's really basic. I highly recommend understanding it. So we say, write the tree, and it gives us back another SHA-1 hash. Right? So far, the only thing Git has done is move files around and give us hashes for the contents of files. It's like nothing special. So let's look at what's in the tree, because if we have a SHA, then we have a file, right? So let's look at what it gave us. It gave us back something. Git cat file -p. So cat the file, printed to the screen. That's the SHA for the tree, and it says 100.644. We know what that is. Blob. Everyone knows what blob is. Big chunk of data. The hash 1F7A7A. We know that one, right? That's our file, and the file's name. So when we said write tree, we just got back a file that has a line that we told it to put there. It's a text file. Again, really basic stuff. It's just the order that this whole process happens in that's complicated. So let's try actually pushing our first commit. So echoing first commit, piping it to Git Commit tree. So we know what our tree is. Our tree is this file that lists other files. So that's our tree's SHA hash, and then it pumps out another SHA-1 hash. This is your commit. So this is a SHA-1 hash that represents everything in your commit. Let's look at that file. Git cat file -p, short SHA. It says tree, gives us the SHA for the tree right here. And it says author is Thomas Rideout, committer is Thomas Rideout, and the contents of the commit or first commit. I wrote a commit log. It saved it as a file, and then named our commit after the file that it saved. So, is everyone kind of following along? Any questions? Terrifying silence. Now, this information got added. I didn't type that information. That information got added by the tool. So we'll see where that happens.
It came from your config file.
It did. So, you could do it this way, or you could just say echo simple commit to the object 1.text, git commit am, which means add, and my message is the easy way, and then it just returns, oh, you did it the easy way. It still returns a hash right there. It still says this is the commit ID that you're on after creating a new commit, but it's quite a bit easier. And this is the thing that we're used to. What we're used to isn't very helpful to us, because we need to understand why these things work. This is why everything works. So git cat file, right? It just says take a file and read it in whatever way you need to read it, but return the output. -p means give it to me on the screen. So read it and then print it. Now the reason that cat file is necessary instead of just catting an actual file is because this part here locates the file, and because the file can be compressed. It can be in a totally different space that we don't have to worry about in this example here. But this is the way you read raw files out of Git. So git cat file -p print to the screen. Master is the branch that we're on. Caret means the first parent. So if I'm on master and I want to know about master, because there's this idea of the tip and the tail. So if I've committed something to master, I'm on the tip. My working directory is on the tip. If I want to know something about the branch master, I have to go to the tail, which is right there. Now it can be, for the first parent, a caret or a tilde. They both mean the first parent. Squiggly brackets, tree. This is a special type of object. So this is the tree that represents the most recent commit on the master. For our example, our tree file looks like this. Object 1, SHA hash, log, permissions. Ultra simple. The commit that I'm on points at a file that tells me how to point at this file so that I read it from a log that is historically accurate. Like I said, I'm not storing diffs. So since I committed, or since I created 2 files and saved 2 files to my Git directory, I need to point specifically to the one that represents what I've got in this Git, in this branch. This is a real life example. This is a basic Laravel application at its root directory. You'll notice a few interesting things. Blob, 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 tree, blob, tree, blob, tree, blob, blob, tree. Okay. Trees have their own permission set, just like in Linux or Unix, whatever you use. Everything has a SHA. And here we see env example. That's our SHA or our example environment file. But here, tree.idea. Let's use an easier one. Database is a tree. So if you know the Laravel system, you know the Laravel file system, you'll know that database is a directory. So how do you represent directories if all you store are flat files named after the SHA of the contents of the files? If you're into old school file system development, you'll recognize that this is a file system. Anything that it can't point to, it points to something that can point to it. Directories here are flattened into files and then stored as files. The contents of that directory are flattened into files and stored in files. So if you rename a file, then this SHA will change. But if you don't rename a file, the SHA stays the same, but the place it points to ends up being different. So everything flows downhill. So we've got our master tree. Remember, this is the Hibbert space. This is the really hard part, which isn't that hard. We've got our main tree, and it just branches out into other trees, which are actually directories. So all we have to point at is a single SHA-1 hash, and now we're pointing at a completed file system that points at every change that has ever existed. So here, our blob, readme.md, our tree resources directory. So now, let's use this tree information. We have tree numbers. So now we can use those tree numbers to create different references. The first reference we look at is branches. So if I say git branch, it just tells me all the existing branches I have. Master, it's my own branch. So if I list the contents of git refs heads, all I see is master. Now if I read the contents of master, I get a SHA-1 pointing at a tree. A tree which is just a flat file in a directory that's got the two first characters snipped off. That's it. Let's screw around with it, right? So we've only got one branch, let's git branch example. So we've created a new branch, git checkout example. Switch to branch example. More git head. It says, currently you're on refs heads example. Head is just a pointer, capital H-E-A-D, is just a pointer to what branch you're currently working on. You could literally open up your text editor, change that from example to master, and now you'd be working on master. You'd screw up all sorts of stuff in your own directories, but now you understand why it'd be screwed up. It'd be screwed up because you're working on files that are way different than they're supposed to be. That's actually not entirely true. We can move that. So let's check out master and more git head. And now it's switched back to ref heads master. Git checkout master just touches a file. It just edits one file. That's all it does. And that's just creation and using of branches. If I were to go to refs heads master, master would point to a tree. When I say git branch example, git checkout example, guess what? Example points to the same tree because it's just a branch. It's just diverged. There's no changes committed yet, so they both point to the same place. So because they both point to the same place, I can't say where I am now based off of what I'm pointing at. I have to have the head file to know that I'm working in a theoretical new area. Tags. Tags are different than branches because they're rock solid. So if I say echo final version to object 1, commit it, and say this is the final revision. And then I say git tag A, which is add all unattached files. Let's name it v1.1, and let's point it towards that commit. So now I have a commit that's tagged. That tag will always point to that commit. And that tag is located in refs tags. And it's just a file named v1.1, and the contents of that file are just 71fcebf, etc., etc. I might just screw up this. A tag just points at a specific commit, and it doesn't change. That's what a tag is. A tag doesn't point to a branch, doesn't point to a release, doesn't point to anything but a tree. you can, in theory, tag a subdirectory, because a subdirectory is a tree. So you could say tag this subdirectory as, API section. And if someone checked out the API section tag, they just get the API section of your code. It just points to a tree. That's all it does. Remotes, another reference type. This is the classic GitHub remote creation tool. We're going to create an account, call it inside Git, and it's going to give us a URL. We're going to take it and say git remote add origin. Now, origin is just a matter of habit. Your names don't matter at all. It could be first, second, third, or blue, or bunny, or puppy. But origin is what people usually refer to as where their code came from in the first place. And then the URL that it gives you. And then you say git push origin master. So push my current Git state. Now this is not my staging or my checked out state. This is my Git directories state to origin on the master branch. So now my master branch to the origin master branch. All my changes get pushed over. All of these things are really super relevant, but we're not going to go over them. And now you can see object 1 is in my remote. Just keeping things basically synchronized. If I view refs, remotes, origins, master, I can see the current state of the remote as a SHA-1 hash in a text file. This is just more. The command here is just what's in the file. You see how basic these files are. It's just SHA-1s getting shuffled around. There's nothing actually that complicated to it until you start getting into the next part. And then the place where this kind of stuff, these changes get stored, is your .config or your .git/config file. This is where your name and your email address and stuff get stored. This tells you what your remotes are currently set to, and this is where these big changes occur. Can we get those backlights back? Throw those back on. Which one's those right here? Getting too dark. There we go. Good, Frank? Picking up?
What's that?
Picking up?
Yeah.
Gotta go now. So, this is just a visual breakdown of branching, something that you think you already know, but we're going to actually stick with the visual elements of why they matter and point at the SHA-1s, because the SHA-1s keep showing up. So, you're on your master branch right now. And when you say head, head says you're on the master branch. It says ref equals master. So that's how you know which branch you're currently on. Head tells you. Master says, well, the tree we're looking at is this tree. So if I echo branch 1 to object1.text, commit it, call it my second commit. Now we have a new tree. Same branch, same head. We're changing the contents of refs master to point to tree FEFE4FA. Right here, FEFE4FA. When I made a new commit, it said this new commit is now in charge of master. Important note here, I should have made it bigger. See that arrow pointing up? When you're drawing this as a graph, you wouldn't think that that arrow would point up. You'd think that one commit leads into the next, leads into the next. But in Git, you can start anywhere. I can make another branch here. But if I wanted to check out this branch, and then I wanted to know what happened before this branch, I would see what this branch pointed at. This tree said, my parent tree is this one. I came from here. So when you're looking backwards in time with Git, you follow the arrow because there's no such thing as forward in time with Git. You can't literally look at the future. So my tree here can't store information about who its child objects are going to be. That would change what the commit contained, which you can't. Not supposed to do. We'll do it later. All this tree knows is who its parent was. Its parent was FEFE F4FA. And it knows who its parent was. 9AC and A. So when you see graphs in Git, yeah, the arrows go backwards in time. They point historically backwards. So let's create the example branch, right? Now I'm still pointed at head. But now I have two files, master and example. These are literally files that point to the same SHA value. Now I say checkout example, and I've moved my head to say ref equals .get refs branches example. I can dance back and forth between these two. Nothing's different because they're both pointing at the same tree. Merging is where it starts to get complicated. And merging is where Git leads you to believe that diffs are used, but they're still not used. So I've created a new feature branch called feature branch. It's very creative. And I've pushed a new commit onto it too. You know, for the sake of brevity, there was a feature on C2, but since I've committed a new commit, now features on commit 3. Master is on commit 1, commit 2. Now somebody else goes in and creates commit 4 on master. I create commit 5 on feature. Now I want to bring us back into uniformity, back together. I want to create C6. Commit 6 is a special kind of commit that you will be asked to perform if there has been a change between here and here. Okay, so if I can't follow the parenting all the way back, if there's something in between, if master isn't still set to C2, then I have to figure out what to do. So what I do is I create a multi-parent merge, or a multi-parent commit. This is a commit that has two parents. My parent is C5 and C4. So looking back here, C5 has one parent, C3. But C6, bringing things back into uniformity, is going to have two parents. I've got to figure out what changed from here to here. So I'm going to look at these three commits. I'm going to look at this as the global parent. So this commit, C2, is the parent to C4 and C5. This is where we both started doing work. So let's roll back all the work we've done on C4 and C5 and C3 to C2. And then let's diff what happened. What changed here? What changed here? And then combine those changes here, if possible. Auto merging, it's not an exact science, but it gets it right almost all the time. Basically says if these two things weren't in the exact same area doing the exact same thing on the exact same files, then we can just apply what changed between these three components and make it a new commit. Now, when you say git merge, it just asks you to comment on the merge. You asked me about this. No, you asked me about it. No, you did. And why is it that every time I commit to master, it asks me for a comment when it just says automatic merge? The last letter from ago? No, you weren't there. Wasn't, no, I know. Well, okay, so the deal is, when you say git merge, you're creating a new commit that contains the work of someone else and you, and it's just saying, I want you to agree. It assumes that it's good enough at what it did, that it's just asking you to say, okay, here's the date stamp, time stamp, my name, I sign off. That's all it's asking you to do. There are conflicts, at which point it will say, here is head, and then here is commit, blah, 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 with name, blah, blah, blah. Which one do you want? But in most cases, it will just ask you to say okay and type in a message. Now, this is where we get into things. This is a super important part, probably completely incorrect. This syntax, I've gone over like 10 times. And if you're getting into it, you've done something wrong. Head is where you are. Head tilde is the first parent of a merge. Head caret is the second parent. Head tilde 2 is the first parent of the first parent. There's an official chart for this, and it's way harder to understand. It's technically correct, whereas this is technically completely incorrect, but you understand what the difference between tilde and caret is. That's my only point, is just know that they mean that you're pointing at the parent of other, because branches can branch and branch and branch. It gets crazy ugly. So you can't say head caret 3 tilde 5 caret 4, and you're weaving your way through the commit log. But at that point, pull up the visual editor and just pick the specific commit and check that one out. So who's seen a Git say that it's fast forward? Who knows what that means? That's right. I had no. I always just saw it say fast forward and was like, good, great. Your master is a file that has a tree SHA-1 in it. And if I were to make a new branch and call it feature 2 and then merge it in without anything new on master, all I have to do is rename or change the contents of the master file to the new SHA-1 for C3. It's a fast forward. I have to do no work.
I think all that's happening is you're moving the head, right?
You're moving the head and you're changing. In a fast forward merge, you're moving the head and you're changing the contents of the master to point to the new tree. So you're literally copying head to .git refs branches master. So you're copying it to the destination branch. It's like the easiest thing in the world to do. As opposed to these complicated merges, fast forward merges just say, oh yeah, straighten the line out. And when you view these things in Git branches, Git charts, you just see it as a straight line. It'll be a different color, but the line just goes straight. There's no two-parent issue, there's no nothing. But
Tell it not to do that. You know what that flag would be sometimes to keep the tree free.
yes,
On a merge.
that's what you were saying, was that the history of what occurred here.
Your history left alone.
Yeah, the
That's
history of
good
what occurred
sometimes.
here between commits can get lost in a fast forward. So you can say no fast forward, which will create a merge log even if you don't need a merge log, because it'll dual parent commit 1. So commit 1 will be parent 1 and parent 2. Rebasing, though, which is something I do a lot, but I know a lot of people are terrified of, does a more complicated process. So I've got commit 1, commit 2. I branched off of commit 1, and I made commit 3 and 4 for my new feature. Now, I'm not in control of master. That's some guy who I have the utmost respect for. I don't want him to look through the massive amount of changes in my merge log. I want to make it the smallest, most concise thing possible for him. So I want to pretend, now that I'm done with commit 4, that I had started on commit 2 in the first place. So rebasing says, move me from here to here. Act like I had been working in a different state completely. This deconstructs everything that happened here. It creates diff files, stores these diffs temporarily, then checks out the latest branch and applies the diffs one at a time. This is like a merge, but it's happening on the client side instead of creating it as a commit on both sides. The problem is the SHA-1 for the C3 tree and the SHA-1 for the C3 tree are now different. If there is a commit 2, then by the nature of how SHA-1 hashes work, this cannot be the same as it used to be. This is where rebasing is dangerous, because I'm literally rewriting history. I'm taking a change log of what I've done instead of what I've actually done as a whole file, and I'm applying it to what I think it should be. I guessed.
Can you explain exactly why it's dangerous? Because I have a colleague that does that, and I was trying to explain why it was dangerous, and I didn't quite understand.
So imagine that you're working on C3, and then you go to commit something, and C3 no longer exists. If someone branches off of C3 in this state, and then commits in this state,
Oh.
So there's official documentation, git-scm.com/docs, or documentation. It says if you want to keep your friends and don't want people to hate you, don't rebase publicly accessible code. This is your danger. And yes, the official docs say, don't do this, don't do this, don't do this. If your code is public, if someone can branch off of your branch, rebasing is the most evil thing you can do to somebody. Because now, when they do a diff between C3 and C1, they get the changes between C3 and C2. And they look at their file, and those changes don't exist, because the file isn't synced up with what they had initially. It's like the paradox of time travel. It's like the Back to the Future alternate universe problem.
So if you're doing your rebasing only on your local machine and you're the only one that uses that, then you're okay.
Yeah, no one can ever fork your branch. You're good. I rebase all the time, because my branches don't get used by anybody else. My branches are always on my local machine, never public. When they're public, and look, this is a 4 commit example. You can imagine the 40 commit example, where someone has branched off of your branch and they threw 12, and then someone branched off of their branch. Like, yeah, those aren't common situations, except that if you're an open source developer, those are really common situations, like painfully common. If you're managing the Linux kernel, which is what this was written for, you don't want someone branch of a branch of a branch of a branch. There's your double-edged sword. The way you don't get someone's branch of a branch of a branch is correct rebasing, proper rebasing. But the way you get someone's branch of a branch of a branch of a branch is bad rebasing. So from here, what's the next step? What do I do to really easily merge this onto master? Fast forward rebase. Right? I don't have to create a commit. I don't have to create a merge commit because there's only one parent. Back here, there'd be two parents. I'd have the parent C2 and the parent C4. But here, I can make it look like I had started in the right place the first time, in the first place. And when you're working in open source, yeah, this is what you want to do. When you're ready to issue a pull request, rebase, check all your code, make it as easy as possible for them to take the merge. Hooks. We're shockingly close to the end. Hooks in Git work differently than hooks in SVN. You get one hook per action, one hook script per action. So if you want to do two things as a pre-commit hook, then you have to have a script that runs two things because they're named pre-commit. If you remove .sample, then all of these will execute. They're basically just named after the command that's executed. When I say git commit, this runs before the commit executes. It's just a script. It does PHP-MD or linting or any other tests you want to run to make sure that they can't commit bad code. Your default git init includes all these scripts, which I think is weird. But yeah, if you go into all of your Git directories right now, there are these sample scripts in all of your projects. Kind of weird. Whatever. Does anyone not understand Git hooking and why that's helpful? There's a lot more. Like, I fully burned out. But what you know is trees. What you know about is how everything is just a SHA-1 pointing to a file, not a diff, a full file. It gets cooler, but you basically know everything there is to know about Git internals now. Everything. So when I go all the way back here, all the way back, all the way. Does this seem kind of like it's making it seem to be harder than it really is? Because that's the point. Do you understand that all you're doing is taking SHA-1s of files, or SHA-1s of files of files? You're not homeomorphing anything. There's no endofunctors. The Hilbert space is a SHA-1 of a file structure. You guys are now as good at Git as it gets to get this journey. That's it. Any questions? Lights? Is everyone okay? No one's talking. Is it too much to get in a single sitting? Well, that's it. Daryl, clap.
You actually did answer my question, or answer something when you asked if I had that question.
Which question?
master, like I get to do another kind of commit
Yes.
on top of that, like I can never do what I can do. So,
2 parents. Yeah, everything's just SHA-1. It's just text files. You can do all of Git in Vim. And with this amount of knowledge, you can do most of Git in PHP. You could probably go just write up SHA scripts that look to files. You know? URI is a real command. It's actually useful. It reports things in minute detail. Blame is my favorite command. You can say blame file name, and it'll say who made each individual change line by line. Log is your change log over commits over time. Show can give you now show is one that's less common, super helpful. You can say show head 2 there, and it'll give you the commit log for 2 heads ago. So it's just a quick way to look back in time. Git flow is a system for feature management, hotfix management, stuff like that. It's a plugin that goes into Git. And all these things, all the Git commands are just shortcuts to other longer Git commands, which just write files and SHAs. GitLab is the free version of GitHub that you can host locally. Common Git conflicts. If you type this into Google, then it will give you a walkthrough on how to solve common Git problems. Which, like, if you're bored and have 2 hours to spend, it's better than a movie. Like, really, like it's fun to actually execute bad commits and screw them up as bad as possible, and you will come away from it having incredibly useful knowledge. And then the doc, gitscm.com/doc, is the most readable documentation for any software development that I've ever seen. The documentation is very good. I kept getting tempted to steal the artwork straight from the documentation, but I decided to learn how to make mine.
Okay, so you skipped sub-modules.
Yeah, I did.
Because you're people.
Yeah.
I
did. I know I did. Yeah, submodules are for if you need another Git project in your Git project.
A couple of them in there, and it's just
Yeah, because Git exists in the root directory of your project, then it doesn't have the greatest knowledge of the vendor directory. So if you use a framework, you're used to the git ignore file, which says ignore vendor. But if you need to work on something in the vendor directory that's not controlled by Composer, then you need to use it as a submodule, which says, hey, I'm here, and don't worry about me. I've got my own shit going on. So submodules are important, but painful.
I'd like to recommend a YouTube video. It's
Yeah.
called, you may have seen it, it's called Git for Ages 4 and Up.
I haven't seen that.
It's amazing. It really explains.
Except 3 teenagers. Nothing to do.
Yeah, it's good. It's good. It's a different approach than you did, from a different angle. So every different approach gives you more knowledge, right? So
Absolutely.
yeah, Ages 4 and Up.
So work with like MIT Scratch and all that stuff for kids.
There's also Learn Git, which is an interactive program by Code Academy. And it's the whole first chapter is free, which the whole first chapter is pretty much beginner Git stuff, but it's an interactive system. It's very nice. More questions? You got a question, right, Frank?
I'm trying to think of something that would be good to ask, but I can't.
What time are we looking at? Did I run short? 8:14.
All right.
That's just about right. But if anyone wants to stick around and listen to the next part, do you know what happens when you take two different files and compress them? You get a diff.
Huh.
Compression algorithms look for things that are the same and things that are different. So when you take two files, you compress them, you end up storing one copy of the full file compressed and one copy of the diff between the two compressed. So the way Git stores files that seems like diffs and isn't any bigger than SVN, which only stores diffs, is that it compresses the data. So if we go all the way back, there's this one place where I said we're going to ignore that directory. It's called pack. Info and pack. Pack is packed files. So remember, I keep saying git cat file is the way we have to call it because we can't necessarily just cat the file directly. Well, Git in its internals, the secret internals that aren't in the book, compresses files on a regular schedule. Makes sure things don't get too big. And when you compress, like I said, two of the same file with differences in them, you end up storing one of the same file and one of the differences. So you end up with no greater file storage than your original diff-based system in the first place. So Git pack is a much more complex version of the Git file system storage, where it compresses everything into clibs and stuff. And whenever you do a Git remote push, then that's when your files get packed automatically. That's when it says you stop working on this, so archive it for future reference. There is a Git GC command. GC is garbage cleanup. And the garbage cleanup system can be manipulated with the Git commands. I've had a situation where I committed a 4 GB file to my Git directory. And it was a 4 GB file of user passwords. And it was like 20 commits ago. It's a long time ago, right? So Git RM doesn't solve my problem. So not only is the file system too big in Git, also storing user passwords permanently in Git. Because anything you put in there, whether or not you RM it later, it's there forever. When you RM it, you're just removing the reference from the tree file. You're just deleting a line from a text file. It's still there. So git GC --prune says if there's any big files that I'm no longer referencing, it's okay to delete them. And delete them from history. Now, deleting them from history means either changing a SHA-1 or not changing a SHA-1 and having it be incorrect on purpose. The choice is yours. Don't do it unless you have to. That's the problem. I mean, all these history rewriting things, yeah, do them the way you want to, but don't do them at all. Like, don't ever do it. You're not supposed to. I had to delete this file because I couldn't push to GitHub, and it had all my users' passwords in it. But there's all sorts of garbage cleanup stuff you have to take care of that gets taken care of for you that you can tweak and edit. And commits are forever, just like diamonds, because people never get divorced. But it's the contract. Commits are forever, contractually. They can be not forever. Rebasing, historical edits. You can check out old commits and change something, and you can have a commit. You know, in my drawing of commit 1, 2, 3, 4, you can insert a 1.5. No one ahead of 1.5 is going to be happy with what you just did. No one. But this is the real world, and sometimes you have to make changes that are going to make everyone happy. So that's what pack is. Pack is the secret hidden targets.
Cool.
I put YouTube videos on. You guys like video game Doki? We still got like 15 to 20. It's all of you, actually.
Oh, yeah, no, it's all good. Whatever you guys want to talk about anything?
Yeah, plenty of time to mingle, have some beers, eat some foods. I gotta pack up anyways. That usually takes. We don't have to flee the building like last time, because I went to go pee and then I came back and everyone was gone.
Robert have to keep everybody out.
No, they just disappeared. I think I bored them all to death. Yeah, for some reason we got an issue with the temperature